when any satellite orbits its central object, here we have a man-made satellite orbiting the Earth, the center of the circle of orbit must be the center of the Earth. You can't just orbit around the North Pole. I mean, you can have a polar orbit, as you see here in the right-hand diagram, but in the polar orbit, you can orbit the poles, but the center of that circle is the center of the Earth. Or if it's an ellipse, the Earth must be at one of the foci of the ellipse. But here we'll just round everything off to circular orbits. Here we have a satellite that's orbiting the Earth, right? In either case here, around the poles or around the equator, or it could be anywhere between the poles and the equator as long as your orbit is centered at the center of the Earth. We want to find the speed of this satellite. We call it the parking orbit. It wants to stay at that altitude. All right, so the 5,000 kilometers here is an altitude. It's from the surface of the Earth. That's the altitude. If you look at the previous page of notes from yesterday, the velocity of any given satellite does not depend on the mass of the satellite. We don't need to know the mass of the satellite here. The velocity equation is the square root of g, capital G, m sub 1 over r. So this is simply a plug and chug problem. The velocity of this particular satellite will be the square root of capital G, which is 6.67 times 10 to the negative 11th, times the mass of the Earth, not the satellite, 5.98 times 10 to the 24th kilograms. The units are good there. It's important to double check the kilograms. Divided by the radial distance. But once again, we have to take the distance from the center of the Earth to where this satellite's orbiting. All right, what's given for us is the altitude from the surface of the Earth. This is what's given from the surface. So we need to add to our altitude the 5,000 kilometers, and I'll do this without a calculator this time. It's 5 million meters, because 5,000, then the kilometers is 3 more zeros. That's 5 million meters. The radius of the Earth is basically 6 million meters. 6,370,000. That's given. That's meters. That's given right about here. Well, right here. That's 4,000 miles. That's the rough radius of the Earth. But 6 million meters. So if I add those two numbers, it's essentially 11,370,000 meters, which in unstandard scientific notation would be 11.4 times 10 to the 6th meters, 11 million meters. Or you can say 1.14 times 10 to the 7th if you want. 11.4 times 10 to the 6th. I'll do an unstandard form right now, just so you get used to doing something in an unconventional way. Anyway, when you plug it all in, you end up with a speed, a velocity, tangential velocity of 5,900 meters per second. Irregardless of the mass of the satellite, it has to have a tangential speed of 5,900 meters per second, which is roughly 13,000 miles per hour. And that's pretty fast. You can go that fast when you have no atmosphere. If you were in the atmosphere, you'd burn up. But this is well beyond the atmosphere. The atmosphere is considered to be about 70 miles thick. This thing is well above the atmosphere. It's somewhere around 3,500 miles above the surface of the Earth, so it won't burn up. But it takes a pretty good amount of fuel to get that satellite up there and get it going that speed tangentially, and then it will maintain this orbit. Once it's in that orbit, it will stay there. You don't need any more fuel. Once it's going that fast, it'll keep orbiting that fast around the Earth. So how long does it take for that satellite from the previous problem to circle the Earth? What's the period? Well, we can use Kepler's third law once again, which is the long way to do it. I'll do it the long way first. And that is t squared equals 4 pi squared over g m sub 1 r cubed. So we're looking for t this case. T squared equals 4 pi squared over g m sub 1, 6.67 times 10 to the negative 11th. That's negative 11 there. Times the mass of the Earth, the thing you're orbiting around. In this case, it's 5.98 times 10 to the 24th kilograms for the mass of the Earth, times your radial distance, which we had from the previous problem, That was 11.4 times 10 to the 6th meters cubed. Once again, we get to cube something. So we multiply this all out, take the square root, you find out that t equals 12,000 seconds. You can leave the answer as that, but if you divide by 60, you end up with t equals roughly 200 minutes, which makes more sense to me numerically. Both the same answer. Either one is fine. But that's just a little over 3 hours for that satellite to orbit the Earth. Now the faster way to do this problem would have been to do it simply by v equals d over t. I'll do it over here on the right hand side. I'll do it in black over here on the right hand side. V equals d over t. We found out in the previous problem that this satellite was traveling at 5,900 meters per second tangentially. That's 5,900 meters per second, equals d, which would be 2 pi times r, its radial orbit. 2 pi r would be 1 time around. That's the 11.4 times 10 to the 6th. 2 pi r, that's one circumference, one trip around, over the time it takes to go 1 time around. So v equals d over t. The 5,900 meters per second equals 2 pi r over t. If you do the calculation there, you once again end up with t equals 1,200 seconds. Same answer either way. Here's a good situation. Calculate the altitude of an Earth satellite which has a period of 1 day. This is advantageous, and it requires a high altitude orbit as pictured here. This is the one we're looking at out here. It's quite a ways from the Earth. You're going to find out that it's almost 1/10 of the way to the Moon. But to have a period of 1 day is good because what that does is it has the satellite stay above the same spot, relatively speaking, as the Earth rotates once every 24 hours, and the satellite rotates or orbits once every 24 hours. If this satellite's above the equator, we call it a stationary or geostationary orbit. It's above one spot above the equator at all times. And if you're kind of near the South America territory or in the Pacific Ocean to the west of South America, this satellite can see the United States of America and communicate, and there are dish network satellites up there that give us TV, that sell TV subscriptions to beam a signal from you from outer space back towards the Earth from these geostationary satellites. That's one good use of these satellites. You have a lot of low Earth orbit satellites, as you see in this picture as well, for GPS, for weather, for other communications and purposes, but these high altitude geostationary orbits are good for staying in one spot relative to the surface of the Earth at any given time. If this particular satellite, high Earth orbit satellite, is not above the equator, it can be a circumpolar, it could be orbiting around the poles, then it would be called geosynchronous. Now there are a lot of international rules that govern how satellites and where they can be. Even though there's a lot of space out there, countries have come together to agree upon where they can or can't put their satellites, at least to a degree, so that we don't have satellites, multi-million or billion-dollar satellites, crashing into one another as they orbit around, because there is obviously purposes. Anyway, let's calculate the altitude of a geostationary orbit. We can start with Kepler's third law once again, and that is t squared equals 4 pi squared over gm sub 1 times r cubed. For a satellite to have a 24-hour period, that's 1 day, we need to calculate that, turn that into seconds. Well, 24 hours, every hour has 3,600 seconds. So in a day, if you do the conversion here, that's 86,400 seconds. We want the period to be 86,400 seconds. That's the standard unit. So we have over here, going back to the left, 86,400 squared equals 4 pi squared over 6.67 times 10 to the negative 11th again, given, times the mass of the Earth, which if you look at the previous problem was 5.98. It's 5.98 times 10 to the 24th kilograms times r cubed. What we don't know here is r. We know everything but r. So the fun part about this one mathematically is you move everything around, use your calculator. The last step would be to take a cube root. And once again, there is a function on your calculator, but what I do is usually raise something to the 0.33 power. If you raise something to the 0.5 power, it's a square root, but if you raise something to the 0.33 power, that's a cube root. Anyway, you might want to play around with that and practice that. Pause this and see if you can calculate it yourself. I've done that. It turns out that r comes out to be 4.23 times 10 to the 7th meters. That's the distance from the center of the Earth. So if I show that on a diagram here, from the center of the Earth to where this satellite would be in circular orbit, it didn't come out well in blue, but in red, all right, that's the distance to the center of the Earth. But we want to know what the altitude is. The altitude of this satellite, what the distance is from the surface of the Earth. So I need to take that radius and subtract, or that distance, and subtract the radius of the Earth. So once again, if I do that without a calculator and just moving the numbers around so I can see it better, that's 42,300,000 essentially meters. The radius of the Earth from the previous problems was 6,400,000. It was 6.37 times 10 to the 6th meters. Anyway, if I subtract those two numbers, I end up with 35 million 900,000 meters. Or if in scientific notation, that would be 3.59 times 10 to the 7th meters. So that's our altitude, distance from the surface of the Earth. That turns out to be about 22,000 miles. As I stated earlier, that's about 1/10 of the way to the moon, roughly speaking. So we don't need to know this, but it's interesting. 1/10 distance to moon. All right, another way this is sometimes spoken of is that it's about 5.5 Earth radii. 5.5 Earth radii. If the Earth's radius is 4,000 miles, 5.5 times 4,000 is 22,000 miles. So in summary, Kepler had 3 laws of planetary motion. The planets, or satellites, orbit in elliptical orbits, planets in particular. They sweep out equal areas in equal times, and this square of the orbital period is proportional to the cube of the average of its radius of orbit.